The second half of the course, which is almost unrelated to the first half. So the midterm will be on the first half only. The last lecture is not included in the midterm. And vice versa. The final will not include the first half. Okay. They are really separated. Last time we had the introduction of the second half. So today's lecture is almost something new. Okay? So feel free to start fresh. Today's lecture is very important. You will find it in homework, final, whatever. I can't test you on it every single occasion. I will do. Okay? So it's very important. Like I said, it has nothing to do from before. You have no excuse not to focus and get it all the way. Okay? No excuse. So the axes of the airplane, X body, Y body, Z body. And we have velocities U, V, W in the body axes. We have aerodynamic forces, large X, large Y, large Z. We have the angular velocity components in the body axes, P, Q, R, rho, pitch, and yaw. And we have the moments, L, M, and N. Okay? I mean, this is the table that we had from before. It's nothing new. Rho, pitch, and yaw. If you have any question, please feel free to stop me. So, last time we derived the equations of motion. So we had this kind of block, rigid body, airplane. So for any rigid body, we're given the forces and we're asking for the motion. U, V, W, the forces Fx, Fy, Fz, and also the moments because we have 6 degrees of freedom. L, M, N, we're talking about the rotation, E, Q, R. And the equations are coupled. It's not, we're solving the translational equations separately and the rotational equations separately. So I'll write down here the translational equation again from last time. So mass times acceleration equal forces. The acceleration we have U, V, W dot plus the centripetal accelerations which we derived last time. The omega cross V term. This is what we derived last time. This is QW minus RV. And here is RU minus PW, and here is PV minus QU equals X, Y, and Z as aerodynamic forces, but also F gravity, which we couldn't write in detail. Although we know its magnitude, that it's mg, simply mg. So this is what we had from before, and today's topic, which is almost separate, has to do with this. We need to write down components for gravity in the body frame. This equation is in the body. The first line is along the x-axis of the body. Second line, y-axis of the body, third line, z-axis of the body. So if you have your airplane like this, this is x-axis of the airplane, right? And this is z-axis. They rotate with the airplane. This is x-axis inertial. It's fixed. It doesn't rotate. And z-axis inertial. This angle is the pitching angle of the body. And gravity simply points downward, right? If this is the case, I can just resolve gravity, mg cosine and mg sine theta, and I'm done. But we don't have only one rotation, we have 3 rotations. So we have something like this. Again, this is y inertial, this is z inertial. With the body, the axes rotate with the body. So this is z body, and this is y body. Okay? So this angle is the roll angle of the airplane. How we roll, how much we roll. Again, the gravity is straight downward, and I need to resolve. It will be mg cosine, mg sine. This is very simple. So if I have a single rotation, I can deal with it very simple with our previous knowledge. But if I have all these rotations combined, it's not trivial. Okay? If you have both rotations simultaneously, not only theta, not only phi by both, then it's not trivial. And this is today's topic. If you have a body that is arbitrarily inclined, in general has any general aptitude, how to write down the gravity, which I know in the inertial frame, it's mg in the z direction, in the inertial frame, how to write it down in the body frame, or in general, how to relate the body frame, xyz body, to the inertial frame, xyz inertia. Okay? Given that the body is at a generic attitude, some generic rotation, maybe yaw, pitch, roll, something like this. Given the body is at this attitude, I want to relate the body frame to the inertial frame. Okay? So this is the goal of today's topic, is to relate the body frame to the inertial frame. This goal in particular, the tools that we will learn and the goal itself is almost separate from anything. You can understand this lecture on its own and solve its own problem, separate from anything. But it's always good to have the bigger picture. How we can use this in our course? Well, to relate the gravity force, which we know in the inertial frame, to the body frame. I need to fill in this column in order to have this set of equations. I cannot simulate the airplane equations of motion now because I have a missing term here, F for gravity. Okay? Any question about the bigger picture? We're going to go and indulge on how to do that. And like I said, the tools that we will learn, I will test you on it on every single occasion. If you go to 241 dynamics, I will test you on it. If you go, it will be tested in the homework, in the final, or whatever. So it's an important issue. The thing is, Euler, as a hypothesis, said that any attitude of a rigid body, please, if you have any questions, stop me. Like I said, so starting from here, this has nothing to do from before, has nothing to do with this, has nothing to do from before. You have no excuse not to get it. Any attitude of a rigid body can be represented by at most 3 consecutive rotations. Okay? This is the hypothesis. So, the thing is, the body is at a generic attitude, something like this. I don't know how the body reached that attitude from the initial position. We initially assume that the body is aligned with the inertia. Okay? And then the body did some maneuver, I don't know what it did, but it reached that attitude. and I want to relate this attitude to the inertial one, okay? And I don't know what happened in between. So what Euler is saying is that, well, you can reach any attitude by at most 3 consecutive rotations. Even if you did 4, 5, 6 in between, I don't care. I can reach the same final attitude by at most 3 consecutive rotations. And the solution is not unique. You can do it several ways. For example, here is a very simple example. If this is an airplane and it's just yaw 90 degrees, okay? So from here, it's just now pointing this direction, okay? You can reach this by simply yaw 90 degrees, or roll 90 degrees, pitch 90 degrees, roll back negative 90 degrees. Finally, I reached the exact same attitude pointing this direction, okay? Did you get this? So either yaw 90 degrees, or roll 90 degrees, pitch 90 degrees, roll back negative 90 degrees. So I can get any final attitude with different rotations. He's just saying that to get any final attitude, I don't care what it is, you can do it by at most 3 consecutive rotations. So I can rotate, say, about the z-axis, which we call yaw. Then I can rotate about the y-axis. Then I can rotate about the x-axis. I can use these 3 rotations to reach my final attitude. That's perfectly fine. This is a legitimate way of doing it. Although the body could have done it in a different way. I don't care about what happened in between for the body. I want to reach the final attitude of the body. Okay? So we may assume that we can get there by rotation about z, about y, and about x. Yaw, pitch, roll. You can do it also the following way. Rotation about z, rotation about y, rotation about z again. Remember, this z is different from that z. Why? If you are here, I have my x, y, z axes, and if you rotate about the z axis, so the z axis remain fixed, and the x, y change. Okay? So in the new set of axes, I have new x and y, and the same old z. Now I'm going to rotate about y, so y is fixed, and x and z change. So the z here is different from the z there. Okay? This x is different from the x in the first set, and so on and so forth. So this z is different from that z. So I can do it z, y, x, z, y, z. I can do it, I can replace this y, maybe z, x, y, z, x, z. So starting from z, starting rotation about z, I have 4 possible combinations. And I can change the starting axis. I can make it y, I can make it x. So I have another 4 and another 4. In total, I have 12 possible combinations. You have 12 possible legitimate combinations to reach the same final attitude. Given a final attitude of an airplane, final angles of airplane, I have 12 possible combinations of reaching that final attitude. Each combination represents 3 consecutive rotations. Okay? And in this course, you are required to replicate the analysis that we're going to do here for any of these possible 12 combinations. We're going to do it for the most standard one, which is the first. This is the standard one that you will find in airplane flight mechanics, in robots, in hydrodynamics, in submarine hydrodynamics, and so on and so on. So this is, we call it yaw, pitch, roll. Sometimes they call it 3, 2, 1, because we rotate about the third axis, then the second axis, then the first axis. Or sometimes they call it ZYX. So assuming that the body did this sequence of rotation to reach the final attitude, although the body may not have done it, but I don't care about what happened in the middle, I just care about the final attitude. Assuming that the body reaching the final attitude this way by yawing, then pitching, then rolling. Okay, if this is the case, let's now relate the final attitude to the initial attitude. So here is the picture that is very important. We have the inertial frame. I will rotate from that inertial, which is also the initial frame. Inertial means fixed, doesn't rotate. I will go from here, first rotation about z. So this is about z of the inertial frame. By an angle, maybe let's call it psi. Then I arrive at some new frame. I rotated about z remains constant, but x and y change. So I arrived at some new frame, let's give it a name. It's not inertial frame anymore, right? Let's give it a name, maybe E frame. This frame is of no importance at all. Why? Because it's fictitious, right? It's something in the middle. I don't know if the body really did this sequence or not, but I'm assuming. So from this E frame, I will rotate about y. So about y of that frame, not the original y, but y of that frame, by some angle, let's call it theta. Here I arrived at another frame, let's call it, say, S. So I rotated about y remains constant, but x and z change. I arrived at this frame, which I'm labeling S. I will do the final rotation. So 3 rotations, one about z, one about y, and one about x. About x. xs. By an angle phi. These angles, psi, theta, phi, we call them Euler angles. Okay? Euler angles. So I will add this column, Euler angles. The roll angle is phi, the pitch angle is theta, the yaw angle is psi. Okay? So here, when I do the 3 rotations, finally I arrived at the body frame.